In this video, we're going to look at double integrals over rectangular regions. In our next video, we're going to look at double integrals not on rectangular regions. So we're going to be able to recognize the function on two variable is an integral over a rectangular region. We're going to recognize some of the properties of double integrals. We're going to evaluate a double integral over a rectangular region by writing it as an iterated integral. And then we're going to use double integrals to calculate the area of a region, the volume under a surface, or the average value of a function over a plane region. So, volumes. Let's talk about some new notation. R is my rectangular region, and it is defined by the AB crossed with CD. What this means is that my X value is going to run between A and B, and my C value is going to run between, or my Y value is going to be run between C and D. And I have these ordered pairs X and Y that come from my R2. So that's all the notations. Nothing really surprising there. We are going to be specifically looking in this section at the rectangular region that is above the XY plane. So we're on the XY plane. The function itself is above the XY plane, where z is my function f of xy. So it looks something like this. From a to b in the x, from c to d in the y, and I have some height to my rectangular region defined by z. And of course, we're talking about positive, so we are above the xy plane, not below. So then if we take that rectangular region in the xy plane and we divide it into smaller n by m sub-rectangles, Rij, with an area of delta A, where the sides of each rectangle is delta x and delta y. Delta A is equal to delta x multiplied by delta y. We start to build Riemann sums. Woo! So I'm going to start with Riemann sums to describe the double integration. So we take our rectangular area, the rectangular region, which is now then here. Each one of these rectangular type shapes will have the height of x, which is found by the x sub ij and the y sub ij into the function, which is of course the volume of one of these rectangular, it's not a prism necessarily, but it kind of looks like one, where I have the volume is going to be delta x, delta y, which is equal to delta A, and then multiplied by the height, which is, of course, plugging those values into my function. And so we're going to first define this as my double integral over my rectangular region of f of xy. The derivative of the area is equal to the limit as m and n go to infinity of this double Riemann sum. So this is nothing new, it's just that we're now in two variables instead of just one. So we're going to use the double Riemann sum to estimate the volume of the solid bounded by the surface, where the surface is defined as z is equal to f of x, which is right here. And the vertical planes, where I've got x is equal to 1 and x is equal to 2. So these are my a and b. Y is equal to 1 and y is equal to 2. That would be my c and d. And of course, by the horizontal plane, z is equal to 0. That is, of course, puts me on the xy plane. So let's go through this process with a double Riemann sum. The first thing we want to do is find my area, my delta A. So I'm going to use delta x is going to be, and it is my b minus a divided by, and we want the m in mine to be 4. So I'm going to use 4 in this direction, and this is going to give me 1/4. M is going to go with my x, and n goes with my y. My delta y is going to be the 2 minus 1 divided by 2. So this gives me 1/2. That means these combine for my delta A, and my delta A is going to be 1/4 multiplied by 1/2, which gives me 1/8. Now I'm going to go ahead and draw the rectangular region so I can get all of the appropriate ordered pairs that I'm going to need. Now in my xy plane, I start with the x value of being 1 and I end with it being 2. Now, of course, I'm not scaling this. It's not to scale, so I'm scaling it to make it easy for me. And then my y values go from 1 to 2. Now in this region, I'm going to cut this in half. And then in this region, I'm going to cut it into fourths. So a half and a half and a half. So each one of my rectangles looks something like this. What I need to do now is I need to figure out what my ordered pairs will be. Now, my delta x is equal to 1/4, or if you want, 0.25. So that is the entire length from here to here. That is the 0.25. However, I'm not using 0.25 because of the fact that that is the entire one, and they're telling me I want to do it by the midpoint rule, so I need to be half of that. So my x part right here, I'm going to call this x sub 1. This is going to be equal to 1 plus half of my width, so 1 plus 1/8. That's what my x sub 1 is. My y sub 1, that's going to go with that, so it's going to be this entire y. Distance is going to be 0.5, but I only want half of that, and so that is going to be 1 plus 0.25. So my first ordered pairs is going to be the ordered pair 1 and 1/8, and my y is going to be 1 and 1/4. So that is my first ordered pairs. I'm going to put these values in here to figure out what my function is for that. So I put in f of 1 and 1/8 and 1 and 1/4 into this function. So I have 4 multiplied by 1 and 1/8. And I'm actually going to go ahead and get my calculator out and write it as a decimal. So 1 and 1/8 is 1.25. So I'm going to write that as 1.25. 1.25. 1.25. 1.125. 1.125 for the x, and then 1.25 for the y. So we have 4 multiplied by 1.125, and then plus 2 multiplied by 1.25, and then I have 8 multiplied by the kind of getting messy already. The 8 multiplied by the x, which is 1.125, and multiplied by the y, which is 1.25. This gives me my first height, and that is it is, plugging this in my calculator, I get 18.25. I'm going to call this F11. And that is the height in box 1. So first row, first box, so it's box 1, 1. So this is F of 1, 1. Now I need to find this next point, and to find this next point, I'm going to take my y sub 2 will be y sub 1 plus my delta x. So this is just like doing Riemann sums like we did before. This is nothing new. It's just we now have ordered pairs to put in. And then my y sub 2 is going to be, I'm just going to go along across the bottom. So my y sub 2 for this one will be the same. Nothing new there, so 1.25. And this is going to be 1.125 plus my delta x, which was 0.25. So my x sub 2 will be equal to, I'm going to go ahead and add those. I get 1.375. So then my f of 1, 2, so first row, second box, is going to be the 1.375 and then my 1.25. And I would put this into my original function again. And when I do that, I get 21.75. And I would continue doing this. And this is rather tedious and rather awful, if you ask me. But I would continue doing this, and so I'd find my f of my first row, the third box, which of course would be the 1.875 and the 1.25, and this ends up becoming 25.25. Oh, actually, this should be the 1.625 and 1.25. And then in my last row, so 1, 4, this is going to be the 1.875 and then the 1.25. I put that into my original function still, and I get 28.75. So now I've found the height on each one of those boxes in the bottom. So I found these midpoints along here, and those midpoints were this, and this one. Now I'm going to do the same thing here. So I'm going to have these, and I would find those boxes. So I'll just do the first one. I'll do it in red. So f of the second row, first box. In this case, my x is the same as the first row, first box, which is 1.125. My y value, my y in that position, we'll call it the y21, is going to be equal to my y1 plus my delta y. And so this will end up becoming 1.75. What is going on there? 1.75. 1.75. So I have 1.75, and I would put that into my original function, and I get 23.75. Now, I would do the same thing for all the rest of those boxes. So a lot. There's a lot going on here. And then to find the solution, and thankfully on the homework, I would just recommend that you use a spreadsheet or something else. The volume is going to be equal to the delta A, which is the same, multiplied by each one of my heights, which we know this is the same thing as my delta A multiplied by my f of x sub I j, and then my y sub I j, which was all of these values that we just found, all of those values here. So my volume, and you can see that I've calculated this for you so you don't have to sit there and suffer through this, is my height, which is 1/8, which we know is 0.125. And then it's going to be multiplied by my f of 1, 1 plus my f of 1, 2 plus my f of 1, 3 plus my f of 1, 4. That's 1, 2, 1, 3, 1, 4. And then back here was the 1, 1. And then my second row, which would be the f of 2, 1, the f of 2, 2, the f of plus f of 2, 3, plus the f of 2, 4. Riemann sums. We freaking love this stuff. When I get done, totally done all the calculations for you, is going to be 27 cubic units, whatever those units may be. So that is by Riemann sums. And you're like, wow, I freaking love Riemann sums. And I'm like, yeah, of course you do. All right, so in the next section, we're going to explore when the region is not rectangular. But right now we are. So we're staying in the land of rectangular. If the function that we are looking at right now is bounded and continuous over R, except for a finite number of smooth curves, then the Dumbbell integral exists, and we say that f is integratable over R. Since delta A is equal to delta x times delta y, or delta y multiplied by delta x, we can express dA as dx dy or dy dx. This means that this double integration can be wrote with respect to x first or with respect to y first. The order in which you do it doesn't matter. However, there's going to be times in which one's going to be easier than the other. Let's take a look at some of the properties. Now, these properties that we get are similar to the properties that we have when we're looking at one variable. The first one is the sum. So if f of x plus xy plus g of xy is integratable, then the sum of these can be broke up. So I can look at first one of the functions and integrate it, and then look at the other function and integrate it. Now, the reason I might want to do this is say that this first piece of the function is better to integrate with respect to y, but this second one that I'm adding to it is better to integrate with respect to x first. So this is why you'd want to break them up. You don't always have to, but you can. This is the rule that allows us to do that. And of course, we have the constant, and this is nothing surprising. Just like in one variable, I can factor out that constant first if it makes it easier for me. Now, if R, my region R, is equal to the union of my two regions, S and T, where there's no overlap between these two, except for maybe the boundaries, then I can break it up. And this is similar to saying, hey, remember in one dimension, say I wanted to go from 0 to 7 of f of x dx, and I found that it was easier to say I want to go from, say, 0 to 3 of f of x dx, and then I would add to it from 3 to 7 of f of x dx. That's what this is doing right here. So then I also get this, I pick up something slightly new, is if my function f is greater than my function g for all ordered pairs in R, then its integration will be larger. So the integration of f will be larger than the integration of g. And then if m, some lowercase m, is less than or equal to my function on R, and it's less than or equal to some larger m, then m multiplied by my region is going to be less than or equal to my integration, less than or equal to m, this larger m, multiplied by my area of my region. And then my last one here is in the cases of f of x can be factored as a product of functions of x and y only, then I can break up my double integration as a multiplication of these two. So this sometimes comes in really handy. Now, this next bit of information is going to make it a little bit easier to integrate, and I kind of talked about it earlier, is that it's going to be easier sometimes to integrate with respect to y than x, or sometimes with x than y. It doesn't matter in terms of the answer. The order that you approach it is going to be the same answer, but sometimes it's going to be easier to do one over the other. So that's an example here where my left example is integrating first with respect to y and then x. And this example here is when I'm integrating with respect to x then y. Notice that I'm going to get the same volume. It's just going to maybe easier than one than the other. Then we get this theorem here that says, suppose f of xy is a function of two variables that is continuous over a rectangular region. We see that the double integral, that's from up above, of f over the region is, again, this is formalizing what we said earlier. It doesn't matter which direction we go first. I can do x with respect to y or y with respect to x. And this is the theorem, and it's going to hold true if f is discontinuous only on a finite number of continuous curves. In other words, f has to be integratable over R. So let's start doing the integrations. As I look at this, and it doesn't matter which one I approach this. I can approach with respect to x, or I can approach it with respect to y. I look to see which one I think may be easier. And I also remember that I can break this apart. So I think I'm going to break this apart. This is going to be equal to, from -1 to 1, from -2 to 2, of 2x dx dy, and then plus from -1 to 1, -2 to 2, of 3y dx dy, and then plus the integral from -1 to 1, from -2 to 2, of 5 dx dy. Now, as I look at this and I say, which one do I think is going to be easier? I personally think that it's going to be easier to start with y on this first one. So in this form, because dx is noted first, these are the limits for dx. Now I've chosen to do this first one with respect to y, so I'm going to rewrite it so it is -2 to 2 of -1 to 1 of 2x dy dx. Now the reason I'm doing this is because I have 2x. With respect to y, that's just a constant. So this is going to be from -2 to 2 of 2xy, where my y gets evaluated from -1 to 1, and then it's going to be dx, and this should be dx. This should be dx. dx. So, and this is dx. Okay. So, well, okay, cool. If I evaluate this part with respect to y, this is 2x multiplied by 1 minus 2x multiplied by -1, right? And so this portion is just going to be 2x plus 2x, which gives me 4x. So just this first term is going to be the integration from -2 to 2 of 4x dx, which is not too bad to do the integration. So this then integrates from, or this becomes 4x raised to the 2 divided by 2 from -2 to 2. So this first term becomes, I'm going to take x squared. This is going to cancel and give me 2. So I have 2, and then I have x squared, which is 2 squared, minus 2, and then I have -2 squared. This gives me 0. Now let's take a look at the second term. So we know that this thing ends up going to 0. So I'm going to take a look at my second term, and I'm going to do it with respect to x first because I'm going to treat 3y as a constant. So then this ends up becoming from -1 to 1 of 3xy evaluated from -2 to 2 dy. So I have 3y multiplied by 2 minus 3y multiplied by -2. And this is going to give me 6y. So this is going to give me from -1 to 1 of 6y dy. And then this becomes 3y squared evaluated from -1 to 1, which is 1 squared minus 3 multiplied by -1 squared, which gives me 0. So that middle term is going to go to 0. So then that only leaves me my last one. So it doesn't matter if I do x or y first because 5 is a constant, so let's just leave it as it is. So this is going to be equal to from -1 to 1 of 5x evaluated from -2 to 2 of dy. Now my 5x evaluated from -2 to 2 is going to be 5 multiplied by 2 minus 5 multiplied by -2, which is going to give me 20. So then this is going to be evaluated from -1 to 1 of 20 dy, which then gives me 20y evaluated from -1 to 1, which is 20 multiplied by 1 minus 20 multiplied by -1. So my final answer is 40. So I was allowed to do this into smaller bite-sized pieces because the rule's up above that says, hey, I can break up this into individual integrations over sums and differences. Now let's take a look at this one. This one is going to be interesting. It's going to involve probably some Maybe integration by parts. Let's not start with that first. Let's break it into its bite-sized pieces. Now I'm going to go from 0 to 1 and 0 to 1/2 of the sine inverse, which is the arc sine of x, dy dx, and then plus from 0 to 1 and then 0 to 1/2 of the sine inverse of y dy dx. Now I'm going to label this. I'm going to start with this one and then I'm going to do this one. So I'm going to start with the first one. I'm going to do something similar to the first one and the second one in the fact that I am going to approach this by considering the variable x. I want to have it initially be a constant. So I'm going to leave this first integration as it is. The second integration, this one here, I'm going to rearrange it, so I'll do that with respect to x first. So let's start with this first one. So here's number 1, this integration. So this is going to integrate to from 0 to 1 of the sine inverse of x, and then it's a y, evaluated from 0 to 1/2, and then dx. Now, as before, I'm going to deal with this piece. So I have y the sine inverse of x evaluated from 0 to 1/2. Because my x is a constant, I'm putting in 1/2. So it'd be 1/2 the sine inverse of x minus 0. So this is going to equal from 0 to 1 of 1/2 the sine inverse of x dx. I don't know off the top of my head what the sine inverse integration ends up becoming, but without looking it up on an integration table, I can do it by integration by parts. So we're going to let u equal the sine inverse of x, and du is going to be 1 over the square root of 1 minus x squared. dv is going to be dx. Then just v is going to be equal to x. So this becomes 1/2 the sine inverse of x, because that is my u, multiplied by x. So let me squeeze in an x there. So this is my u and this is my v. So I'm doing this by parts. And then minus the integral, and don't forget the 1/2 there, so minus 1/2. The integral from 0 to 1 of, and then I have x over the square root of 1 minus x squared dx. Now, this is just a regular u substitution. So we're going to say let u equal my 1 minus x squared. That means du is going to be equal to negative 2x dx. And I've got an x and I've got the dx, so negative 1/2 du will replace the x dx. So then this portion right here becomes negative 1/2. Negative 1/2, that was a terrible 1/2. So negative 1/2 integrated from 0 to, oh, I better change those in a minute. And I will. And so I have to adjust for this negative 1/2, and then it'd also be 1 over u raised to the 1/2 du. Now I'm going to change my limits of integration here. Don't forget these limits. I still need to put the 0 and 1 there. I almost forgot that. So when u is equal, well, actually I start with x. Change my limits here. So when x is equal to 0, u would equal 1. When x is equal to 1, u would equal 0. So then this switches from 1 to 0. Then this then becomes, with this negative multiplied by this negative, which is positive, and then I flip the limits of integration, so it ends up becoming negative again, of negative 1/4 from 0 to 1 of u raised to the negative 1/2 du. Now this then becomes negative 1/4, negative 1/4, 1/4. And I have u raising it to 1/2. So then I'd multiply it. So I'd multiply by 2, u raised to the 1/2 from 0 to 1. I put in the 1 because the 0 will make it go to 0. And so I end up with this becoming negative 1 over 2. So all of that just to tell me that this thing in all of its glory is equal to negative 1/2. Now, I do need to evaluate my first 1/2 x sine inverse of x from 0 to 1. So doing this evaluation, I have 1/2 multiplied by 1, the sine inverse of 1, and then I end up with minus 0. So that's kind of nice. Now the sine inverse, this is equal to pi over 2. So I end up with 1/2 multiplied by pi over 2, which gives me pi over 4. So all of this work to tell me that number 1, just that part of the integration, is going to be equal to pi over 4 and then minus 1/2. So where I am is that this is equal to pi over 4 minus 1/2. That part is. Now I'm going to go through the same process, but with the x's and y's switched around. So we found this first value of this first integration. Let me just go over here and erase so I can give myself some space. I'm just going to go over here and erase all of this lovely stuff so I can give myself some space to do the second integration. Now, this integration isn't difficult. It's just a lot of work because we're now bringing in everything that we did in Calculus 2. So now working with number 2, I'm going to switch my integrations so I can avoid doing the integration by parts until the end. So I'm going to integrate from 0 to 1/2, and then I'll start with the first integration from 0 to 1 of the sine inverse of y, and then dx dy. This allows me to do the integration from 0 to 1/2 of x, and then it will be the sine inverse of y evaluated from 0 to 1 dy. So this portion then becomes 1 times the sine inverse of y minus 0. So this is equal to 0 to 1/2 of the sine inverse of y dy. We're going to have to do the same thing. We're going to have to do the integration by parts, and I should have not erased it, but let's just go through it again. So we're going to let u equal the sine inverse of y. du is going to be 1 over the square root of 1 minus x, or y squared, excuse me. This will be y squared. Y squared. Y squared. dv is going to be equal to dy, and that means v is equal to y. So then this goes to the y, the sine inverse of y, evaluated from 0 to 1/2, minus from 0 to 1/2 of y divided by the square root of 1 minus y squared dy. And you're thinking, oh, yay, we're going to do another u substitution here, and you're right. We're going to let u equal 1 minus y squared. du is going to equal negative 2 y dy, so negative 1/2. du is going to equal y dy. And of course, when y is equal to 0, u is equal to 1. When y is equal to 1/2, u is going to equal to 3/4. Is that right? So 1/2 squared is 1/4. 1 minus 1/4 is 3/4. All right, so negative 0 to 1/2 of y, the square root of 1 minus y squared, dy becomes negative from the lower limit of 1 up to 3/4, negative 1/2, u raised to the negative 1/2, and du. Okay, double negatives make it positive, and then of course when I then switch the limits, it will then become negative again, so negative 1/2 from 3/4 to 1 of u raised to the negative 1/2 du. So then this is going to be equal to negative 1/2, and I'm going to add 1, so that becomes u to the 1/2, and then I divide by 1/2, so multiplied by 2, u raised to the 1/2, evaluated from 3/4 to 1. This becomes negative u raised to the 1/2, evaluated from 3/4 to 1. So negative, and I have 1 raised to the 1/2 is 1, and then minus 3/4 raised to the 1/2, so it'd be the square root of 3/2. So this is going to become negative 1 plus the square root of 3/2. That's that part. Now, so this, just this piece, is negative 1 plus square root of 3/2. We do need to evaluate this, so let me do this evaluation down here. So this evaluation is going to be 1/2 the sine inverse of 1/2, but the sine inverse of 1/2 is pi/6, so 1/2 times pi/6. So then this becomes this entire thing, number 2, becomes pi/12, and then minus 1 plus pi square root of 3/2. Square root of 3/2. Now, that means this over here is going to be pi/12 minus 1 plus the square root of 3/2. This equals pi/4 minus 1/2, and then plus pi/12 minus 1 plus the square root of 3/2. Give myself some space, clean this up. So all of this work to say, so I have pi/4 have the same common denominator, so 3 pi/12 plus pi/12. This gives me 4 pi/12, which gives me pi/3. So these two are going to give me pi/3. And then I have negative 1/2, which is the same thing as negative 3/2 plus the square root of 3/2. So then this becomes plus the square root of 3 minus 3 all over 2. And that is my final, yet delicious, scrumptious even, answer. Whew. The integrations in and of themselves are not terrible, but we're just adding just a little layer here. So I would recommend you might want to go and refresh the integration by parts, or some other topics that you may not have felt completely comfortable with in Calculus 2, because they will rear their lovely head now. Just something to think about. Now let's see if my next one is a little bit easier. And so I'm going to be doing this integration, and I just want to erase some more of this work up here so it doesn't look as cluttered. Okay, so I'm going to integrate e to the x plus y dy, and then with respect to x. Now, I don't think that this is going to save me any work to do one over the other, with the exception of maybe doing the natural logs first. So let me rewrite this to make it maybe better. And the only reason I'm doing this is because I see the natural logs. So I'm going to integrate this from 0 to 1, and the integration of the natural log of 2, the natural log of 3, of e to the x plus y, and then it's a dx first, because the dx goes with these, and then dy. Now this then becomes, well, e to the x is e to the x all day long. E to the xy is going to be e to the xy. Its derivative would be e to the x, and then the derivative of x plus y is just 1 because the y is a constant. And so this is just going to be from 0 to 1 of e to the x plus y evaluated natural log of 2, the natural log of 3 dy. So it's already looking a little bit better. Now, looking at just this part, I have e raised to the natural log of 3 plus y minus e raised to the natural log of 2 plus y. This is equal to e raised to the natural log of 3 multiplied by e raised to the y minus e raised to the natural log of 2 multiplied by e to the y. And that's because if my exponents add, I must have multiplied my bases. We have this rule that says if I have the base raised to the log base b of x, this is equal to x all day long. So this goes to 3, this goes to 2, and what I end up with then is 3e to the y minus 2e to the y, which ends up just being e to the y. Oh, isn't this sweet? So this is equal to, from 0 to 1, of e to the y dy. After our last one, this is lovely. So then this just becomes e to the y evaluated from 0 to 1, which is e to the y, which is e to the 1, e to the 1 minus e to the 0 is 1. Look at that. Oh, that's so sweet. That last one, not so sweet. Okay, now let's take a look at this one. I'm going to erase, give myself some space and think, oh my gosh, that was so lovely. After that last one, please let this one be nice. Please let this one be nice. Okay, lock rotation. And as I take a look at this, and I'm thinking, it doesn't look nice. It doesn't look like my best friend. It doesn't look like this is a good time. Let's integrate with respect to x first. And the reason I'm doing that is because the derivative of 2x plus y with respect to x is going to be 2x. So let's switch these integrations. So this will be 1 to 2, 0 to 1, x of x squared plus y squared dx dy. So then I say let u equal x squared plus y squared. Du is going to equal 2x dx. That means 1/2 du is going to give me x dx. Now I am going to go ahead and change my limits here. If x is equal to 0, u is equal to y squared. If x is equal to 1, u is going to equal to 1 plus y squared. So this is going to integrate from 1 to 2 of the, let me see. This will integrate from u squared, or y squared, 1 plus y squared. And I have 1/2 my u du, 1/2, excuse me, 1/2, and then 1 over u, because that's what x squared plus y squared was, du, dy. So then this becomes from 1 to 2 of the natural log, so this is the natural log, I'm going to bring that 1/2 out front. The natural log of u evaluated from y squared and then 1 plus y squared dy. So then working on just that part, the natural log of 1 plus y squared minus the natural log of y squared. All right. So then this becomes 1/2 from 1 to 2 of the natural log of 1 plus y squared minus the, well, I'm going to use the rule that says this is going to come out front as a multiplier, so that'll be 2, the natural log of y dy. So I'm going to go ahead and break this apart. So 1/2 from 1 to 2 of the natural log of 1 plus y squared, and then minus, and then when I distribute this 1/2 onto that 2, that will cancel itself out, from 1 to 2 of the natural log of y dy. And you're thinking, integration by parts, anyone? And we're going to say, oh, yes, lovely, thank you. So we're going to start with this one first. Do this one in red. I have let u equal the natural log of 1 plus y squared, and du will then equal 1 over 1 plus y squared multiplied by 2y dy. And then v, don't forget my dy right there. dv is equal to dy. That means v is equal to y. So I have 1/2, and I have y, and then the natural log of 1 plus y squared, evaluated from 1 to 2. And then, this is awful, let me clean this up just a little bit. dy, dy. Okay. And then I'm going to have minus the integration of 1 to 2 of y, because that's my v. And then I have 2y, 1 plus y squared dy. Now this, I'll go ahead and work with this for a moment, and then I'll look at that other loveliness. So I have 1/2 multiplied by 2, the natural log of 1 plus 4, minus 1/2 multiplied by 1, the natural log of 2. So I have the natural log of 5 minus 1/2 the natural log of 2. Okay, so that's that part. Now I'm going to have to do something with this. As I take a look at this, this is going to be 1 negative from 1 to 2 of 2y squared, 1 plus y squared, and dy. I think I'm going to do some long division here. So the reason I want to do long division is because I have y squareds. They are in the numerator and the denominator. So I'm going to do y squared plus 1 divided into 2y squared, and then plus 0y plus some constant of 0. So to make these match, I need to multiply by 2. And when I multiply by 2, I have 2y squared plus 2. Subtract that off. And so this is going to give me 2. So 2y squared over 1 plus y squared is going to be 2 plus, oh, that should be a negative, negative 2 over y squared plus 1. So this is going to be equal to, from 1 to 2 of 2 minus 2, and there's a minus out there up front, y squared plus 1 dy. So holy smokes, this takes everything almost we ever learned in calculus 2. in all of its glory. So it's actually kind of really nice, but also kind of not. And so this is negative 2 from 1 to 2 of dy plus 2 from 1 to 2 of 1 over y squared plus 1 dy. So this just becomes negative 2y evaluated from 1 to 2. This becomes 2, and then this looks like the tangent inverse of y evaluated from 1 to 2. Good times, good times. So this is equal to negative 2 times 2 minus negative 2 multiplied by 1. So this is negative 4 plus 2. This part is negative 2. And then I have 2 times the tangent inverse of 2 minus 2 times the tangent inverse of 1. Well, this is going to be minus 2 pi over 4. So this gives me minus 2 over, so minus pi over 2. This is just 2 the tangent inverse of 2. All right, so where the heck are we? That's just the first one. That makes me want to cry. Okay. So this first integration is going to be this. The natural log of 5 minus 1/2 the natural log of 2. Minus 2. Minus 2 the tangent inverse. Minus 1/2. That's just that one. Let's do the next one. Give myself some space. I really tried to choose ones that would be interesting. I just didn't think when I chose them randomly that they would be this interesting, but we got this. We got this. It's a nice refresher. So now let's deal with this piece. So I have negative from 1 to 2 of the natural log of y dy, and this is going to be nice for integration by parts because I'm going to let u equal the natural log of y, and du is going to be 1 over y dy. And then v dv is going to equal dy. That means v is equal to y. That means that negative from 1 to 2 of the natural log of y dy ends up becoming y, the natural log of y, minus the integral of, don't forget that negative out front. So that's going to make that negative, and it's going to make this one positive. So negative, then positive from 1 to 2 of y, 1 over y dy. Oh, that's not too bad. Don't forget to integrate, to do the evaluation from 1 to 2. So then this is going to be negative 2, the natural log of 2. The natural log of 1 is 0, so I don't have to worry about that part. And then this just becomes, oh, this is so nice. This just becomes 1, so I'm really integrating 1, which is really just going to be y evaluated from 1 to 2. So I end up with a negative 2, the natural log of 2 minus, or plus 2 minus 1. So I end up with negative 2, the natural log of 2 plus 1. So that one's not that bad, all things considered. So then let me put that in here for the second piece. So this ends up becoming minus 2, the natural log of 2, and then it ends up becoming plus 1. So we get some cancellations here. The natural log of 5 is not going to do anything, so that's just going to stay as is. So I get, waiting for this to, okay, the natural log of 5. I have 1/2 minus 2 more, so that is minus 5 over 2, the natural log of 2. That takes and cancels those two. And then I have minus 1, that cancels this one, and then minus 2, the natural log. Second natural log, it's tangent. Tangent. Inverse of 2 minus pi over 2. And there it is in all of its glory, provided, of course, I didn't make any mistakes anywhere. But I believe that's what we end up with. I probably made some sign errors. Check my math, and we'll go over it in class tomorrow. I feel like I did some sign errors on that one. I feel like that was just so much fun. Okay, so application of double integrals. We can use double integrals to find the area of a region bounded by the curves of functions. Right now, we're just looking at rectangular shapes. We will go in the next section where it's not, but right now, let's say that we're looking at a rectangular shape. So the area of a region is going to be the double integral of 1 dA. So if they're asking me to find the area of the region, where I'm going from 1 to 4 and 1 to 5, this is simply going to be asking me to integrate from 1 to 4 and 1 to 5 of 1 dy dx. Now, I could have done it the other way. I just started with x first. It doesn't really matter. So then this is going to be an integral from 1 to 4 of y, evaluated from 1 to 5 of dx. This is going to be pretty nice. So we have y from 5 minus 1 is 4. So this is integral from 1 to 4 of 4 dx. And so this will end up becoming 4x, evaluated from 1 to 4, which gives me 16 minus 4. So my answer is 12. And this is the area, find the area of the region. So it's units squared. Okay. Let's take a look at the volume. So we can also do this with volume. For this one, we're going to look at the volume of the solid underneath this z value, and bound by my x going from 0 to 2 and my y going from 0 to 2 as well. So what they're asking me to do is to integrate this from 1 to 2 and, 0 to 2 and 0 to 2. The square root of 4 minus y squared. And I am going to choose to do my integration with respect to x first, because I can. So dx dy. So the 4xy is going to be constant, so this is going to be integration from 0 to 2 of the x 4 minus y squared, evaluated from 0 to 2 of dy, which is from 0 to 2 of 2, 4 minus y squared, dy. So that's not too bad. And so then what I'm integrating is pull a 2 out from 0 to 2 of the square root of 4 minus y squared dy. And you're thinking, this looks like a lot of fun. Well, okay. This integration we can do by, and you're thinking, trig substitution. And so am I. I'm thinking, yeah, this looks like trig substitution. So let's build our triangle. So I'm going to put, let me see, 2 here and y here, and then this must be the square root of 4 minus y squared, which then I have the sine of my angle is going to be y over 2. That means 2, the sine of my angle is equal to y. I also have the cosine of my angle, which is going to be 2 over the square root of 4 minus y squared. So square root of 4 minus y squared is equal to, or times the cosine. That actually should be the other way around. I'm just so excited about, trig substitution. Square root of 4 minus y squared over my radius, which is 2. So 2, the cosine of theta, is going to equal to the square root of 4 minus y squared. Of course, I have the tangent of theta, and that's going to just be, not nice, y over the square root of 4 minus y squared. Okay, so I think I'm ready to start doing my trig sub. So then 2, the cosine of theta, is going to equal dy. Okay, so this is going to be equal to, I have 2, and I have some limits I'll have to deal with the limits of integration in a minute. I have 4 minus 2, the sine squared of theta, and then it's going to be 2, the cosine of theta d theta. I'm just going to call this A and B for now. Then with my trig sub, I have got, and that should be 4. That should be 2 the sine of theta, the quantity squared. So this is going to be 4 minus 4, the sine squared of theta, which is going to be 4, 1 minus the sine squared of theta, which is going to be 4 multiplied by the cosine squared of theta, which then gives me, taking the square root, gives me 2 the cosine of theta. So then this is equal to 2, the integration from a to b, and I'll deal with those limits in a minute, of 2 the cosine of theta multiplied by 2 the cosine of theta d theta. Nice review of trig sub. So this is going to give me 8 from a to b of cosine squared theta d theta. Power reduction formula, because, you know, we love those too. Cosine of 2 theta is equal to 1/2, and then 1 plus, cosine is plus, yeah, 1 plus 1/2 the cosine of 2 theta. So then this becomes 4 from a to b of 1 plus 1 the cosine of 2 theta d theta. The reason that's 4 is because I can factor out 1/2 out of both of these, and then 8 times 1/2 gives me the 4. Now this then becomes 4 theta, and then the derivative of the cosine of 2 theta, to get 2 theta, I must have started out with the sine of 2 theta, so d theta of sine 2 theta, but that would give me 2 the cosine of 2 theta. I'm missing the 2, so then this is going to be plus 4 times 1/2, so that's going to be 2 the sine of 2 theta. And then it would be evaluated from a to b, but I don't want to do that from a to b. So, because I didn't do the trig sub, well, I might have to do the trig sub. What I do know is, let me see, I didn't have, did I want to do that? No, we're going to worry about the angles in a minute. Okay. So I'm going to rewrite this as 4 theta plus 2. Double angle for sine is sine 2 times the sine of theta, the cosine of theta, evaluated from a to b. And you're like, why did I do that? Well, here's the thing. Now, if you remember, the sine of theta was equal to my y over my r value. My cosine of theta was equal to the square root of 1 minus y squared over my r. And if you remember, my r happened to be 2. So I'm going to erase this and write 2. So 2. And this happened to be 4, I believe. Was that 4 or was that 2? It was 4, yep. So then what I really have, oh, and I should probably say that the sine of theta, so then theta is equal to the sine inverse of y divided by 2. Okay, so where am I? Well, I have my, erase all of this. This entire thing is going to be equal to, waiting for that to catch up, 4 times theta. And then I had plus 4 the sine theta cosine theta, evaluated from A to B. But sine theta, so 4 times the sine inverse of y divided by 2, evaluated from, and I can go back to what I had, which is 0 to 2. And then plus 4 sine theta gets replaced with y over 2. Cosine of theta gets replaced with the square root of 4 minus y squared divided by 2, evaluated from 0 to 2. So looking at my first one, I have 4, and then I'm going to put in 2. So this will be the sine inverse of 1 minus the sine inverse of 0. Sine inverse of 0 is equal to 0. The sine inverse of 1 is pi over 2. So I have 4 times pi over 2. And then this is going to be 4 multiplied by 2 over 2. And then I'm going to have the square root of 4 minus 4 over 2. Oh, that's 0, so that's nice. And then minus 4 multiplied by 0 and everything else, so that goes to 0. So my answer is this. Units squared, or cubic units, of course. So 2 pi units cubed. All right, let's look at some more examples because this is some good times. So let me erase all of this so I can give myself some space. And let me go ahead and zoom on in. Zoom on in, zoom on in. Okay, so now what we're going to be looking at is find the average. And just like in one variable, the average, I can find the average of the function. It is going to be 1 divided by the area of the region. So that's just going to be the regular multiplication of the areas. So in other words, this length and this length multiplied together. The length from here to here is 1. The length from here to here is 2. So my area of R for this example is going to be the easy part. It's going to just be 1 multiplied by 2. So that's the easy part, which is 2. What I'm going to do now is I'm going to integrate this thing because they're asking me for the average area. So I'm integrating from 1 to 2, and then, from 0 to 1, 0, from 0 to 1, and then from 0 to 2 of this hyperbolic sine h plus the hyperbolic sine of y. And I defaulted to dy dx, but it doesn't really matter. What I'm going to do is I did before is I'm going to go ahead and I have the 1/2 out front because it's 1 divided by the area, is I am going to break it up and then, of course, choose one and then the other. So I'm going to start with breaking it up, and I'll do this one with respect to y first, and I'll do this one with respect to x first. So I have 1/2. I'm going to do this with respect to y first. So it's going to be 0 to 1 and 0 to 2 of the hyperbolic sine of x dy. And then I'm going to do the opposite. So from 0 to 2, don't forget the 1/2. And then from 0 to 1 of the hyperbolic sine of y dx and dy. And don't forget I need to have the dx right there. So as before, because I am doing the integration with respect to y first, then I end up having 1/2 from 0 to 1. The hyperbolic, so it'll be y, the hyperbolic sine of x evaluated from 0 to 2 dx. And then I'm going to have plus 1/2 from 0 to 2 of x, the hyperbolic sine of y evaluated from 0 to 1 dy. So that's the easy parts. And then when I put in my 0, that ends up going to 0, so that's nice. So this is going to be 1/2, and it's going to be 2 the sine, hyperbolic sine of x dx. And this will also be 1/2 from 0 to 2 of the hyperbolic sine of y dy. Now, the hyperbolic sine, its antiderivative is a hyperbolic cosine. So that's kind of nice. That's nice, right? We can have a nice one every once in a while. So this is going to be the hyperbolic cosine of x evaluated, and then don't forget I need the 0 to 1, evaluated from 0 to 1. This 1/2 and this half cancel themselves out. And then I'm going to have plus 1/2 the hyperbolic cosine of y evaluated from 0 to 2. So this is the hyperbolic cosine of 1 minus the hyperbolic cosine of 0 plus 1/2 the hyperbolic cosine of 2 minus 1/2 the hyperbolic cosine of 0. And we can see that the hyperbolic cosine of the zeros end up adding up. And so I end up with the hyperbolic cosine of 1 plus 1/2 the hyperbolic cosine of 2 minus 3/2 the hyperbolic cosine of 0. The hyperbolic cosine of 0 happens to be 0. So I have the hyperbolic cosine of 1 plus 1/2 the hyperbolic cosine of 2, and that is my final answer. Now let's take a look at my very last example here, wherever that went to. Here it is. So we're asked to find the average value of the function over these level curves. We are looking at a region that is from, in the x direction, from point 2 to 1. So I'm going to start here at point 2, and I go to 1. So I'm looking at this region for my x's. In my y's, I'm going from 0. So my y's, I'm going to go from 0 to 0.8. So this is my rectangle that I'm looking at. They're telling me that my rectangle needs to be in the x direction. Oh, and the y direction is going to be the same. So it's going to be broken into two rectangles, two subrectangles in each direction. What I want to do is I want to find my midpoints for, because they're asking me to do it by the midpoint. So I need to find where my x and y are in each one of these. And I know you're thinking Riemann sum and how excited you are about that. We'll get there. All right, so first thing I want to do is figure out what my x and y here, and here is. So the first thing I'm going to do is find my width of my rectangles. So I have 1 minus 0.2 divided by 2. This is going to be my delta x. This is going to be 0.8 divided by 2, which gives me a 0.4. So my x is going to be broke up right here at 0.6. And then I'm going to do the same thing for my delta y. So my delta y is going to be the 0.8 minus 0 divided by 2, which gives me, again, 0.4. So let me redraw this a little bit better. So then this is going to be cut right here at 0.4. Now, to find this ordered pair, I can see that my ordered pair, this first one right here, looks like it'd be 0.4, comma 0.2. My second ordered pair here looks like it's going to be 0.8 and then 0.2. This one here looks like it's going to be 0.4 and maybe 0.6. Looks like it's 0.6, should be 0.6, yeah. So 0.4, comma 0.6. 0.6. And then this last one is going to be the 0.8 and then 0.6. All right, now, the reason I did all of that is because since I don't have the function, what I have to do is I have to look to see which curve is the closest. So my area is still the same. My dA, my delta A, is going to be my delta x multiplied by my delta y. Now remember my delta x, which I just erased, was 0.4, and my delta y was also a 0.4. So this is going to be a 0.16. Now I'm asked to find the average of this. So I still do my integrations like I did before. I'm still going to be doing the integration of my function with x to y, the dA, and I'm still going to divide by the area of my region. So for this, my area of the region is going to be equal to the length I traveled, which is 0.8 in the x, and then the length I traveled in the y, which is also 0.8, which is 0.64. So we know what that value is. We have to figure out this value, and the way we're going to do it is Riemann sums. So I know what my delta A is, my delta A, and then it's going to be multiplied by, and this would normally be my f of 1, 1, plus my f of 1, 2, plus my f of 2, 1, 2, 1, 2, 1, plus my f of 2, 2. Now, I don't know what my f is, so I have to figure it out by my level curves, and I'm going to go to the closest one to my ordered pairs. It looks like this is where I am, so it looks like this curve is the closest one. So that colored one looks like it is 1/8. So this gets replaced with 1/8. This is my next curve, and it looks like the closest one there is 1/2. So this gets replaced with 1/2. 2, 1, this is my level curve, and it looks like the closest one to that is this. So this gets replaced with a negative 1/8. And then I'm looking at 2, 2, so right here, and my closest one looks like it's 1/4. Looks like this is the closest one. So I would add this up. So I have 1/2 plus 1/4 gives me 3/4. And then, of course, my 1/8 and my negative 1/8 cancel themselves out. My delta A is going to be 0.16. So I found what this is. This is equal to 0.16, my delta A, and then multiply by 3/4. Then I'm going to divide by my region, which is 0.64. And so my final answer is going to be 0.16 multiplied by 0.75. And then divided by 0.64, which gives me 0.1875. So that is the average in this level curve. And there's some really great applications for this if you take a look in the book. We will see you tomorrow in class and go over any questions you have. And this is a very long video, because the examples were long. So, yay! We'll go over this stuff tomorrow in class.